Yeah, so my name is Scott McCarty, and I am a technical product marketing manager for Red Hat, and I work on container engines and runtimes. That's like what I'm dedicated to. So basically, that means I work with all the engineers and then run things, talk to customers, explain how these things work to certain people, like do some of these things. But mostly, I'm driving the roadmap for like what we're going to invest in next and what we're going to do like in the different communities.
Cool.
And then I'm beta tester number one when things don't work.
Okay. Well, we'll have plenty of questions for you, but I'll let you present first, and then we'll take the question. Is that okay with you?
Yeah, that's fine. So I have a mix of some slides and demos, basically, and the slides are pretty much just they're pretty much just technical slides. So let me actually, oops, I should share my screen before I go into present mode. Let me see if you can see this okay. Can you see that okay? And then when I go over to the command line, can you see that okay?
Yep.
Well, I'll clear that out and we'll do this from scratch. Go to that. But before we go into the first demo, though, I will jump back and oops, I didn't start at the beginning. So yeah, I already introduced myself. You know, I have a background in computer science and anthropology. I didn't mention that. So I jokingly say I'm aspiring anthropologist, computer scientist. But basically, yeah, that's why I probably am a decent product manager. I basically kind of live in between these two worlds. So this basically covers there's kind of three main types of content in here. There's like drawings, and then there's demos, and then I'll have some joking trick questions for fun. And then I just start with a basic premise so people kind of understand what a container engine and runtime do basically together. In fact, I talk about just a container engine here, but you know, in a nutshell, a container engine does three main things, and it seems like it's actually quite simple, but yet I get a lot of questions around this and a lot of misunderstandings, and so that's why I try to break it down super simple. Essentially, if you think about CRI-O or containerd or docker or podman or any other container engine, what I refer to as engine, and I make it very distinct so that people can understand it clearly, is it provides a user interface, right? Whether that user is a human, so something like podman or docker is definitely a human interface, or whether it's CRI-O or containerd, which are more, I would call them for robots. You know, they provide an API for robots to come in and talk to them, like the kubelet. And then the container engine has to essentially initiate the commands on the operating system to mount storage, and then it creates configs, and then it passes these configs off to what we call the runtime. And all of these things are basically governed by the OCI standards in different ways. So, like the way the image is getting pulled, you know, I call that part of storage. Essentially, is what I can include that here. And then the way it gets expanded on disk, the way it hands off this config file to the runtime, all of these things are basically governed by OCI, so Open Containers Initiative standards. And so in this demo, I will show you Docker and Podman, but then if we have enough time afterwards, I may do a little extra, like extra bonus content with kata as a different runtime, and then also crun. Well, you'll see crun actually in this, even though you won't realize it. All right, so let's jump right in. So the first one, I call this the discerning container connoisseur. So if you look at like regular Linux processes, Bash, you know, you basically see that Bash basically talks to Linux kernel. It does an exec or a fork, and then basically a process gets created. And then if you look at something like Podman, and honestly, you can fill in Docker here as well. It doesn't matter. Or containerd or CRI-O. Really, there's a human or another robot that comes in and talks to that API. It obviously, you know, does a fork or exec of a runtime, which is in this case runc most of the time. 98% of the world's using runc, but again, it could be crun, it could be kata, it could be gvisor, it could be anything. And then that somehow either goes to talk to the kernel to fire up some kind of process, be it a virtual machine process or an actual real Linux process, and then it runs the container inside. You know, or essentially the container fires off, whether it is directly that process or indirectly. And so side by side, when you think about it this way, you realize that like basically containers are just fancy processes. There's really nothing that magical to them. And so I will then I will show you this. So we're going to run a Podman. We're going to do these as root, I want to point out, at first, and then we're going to do things not as root later for fun. But if you look at this, we're sudoing. I'm actually logged into this Fedora box as myself, Father Linux, and then is my user. And then basically I'm showing you, I'm going to do a sudo here, but let's just run bash in the background with Podman, then let's run it with Docker. You'll see we get back, these basically hashes, if you will, or IDs. And basically these are just user space definitions for these processes, right? Like we're essentially creating another definition of what this process is, and that's what we call a container. That's what humans call containers. But now let's look at these things as Linux processes. So I jokingly show here, like, it's really difficult to tell which one of these was started by Podman and which one was started by Docker, other than maybe the fact that the IDs are later. So you kind of know, since you got to see me start them, you know which one I started first. But if you were to look at this, if you were to like SSH into a server and just do a ps-efz, you'd look at this and you would see, oh, these processes look pretty much identical. Like you wouldn't really know what they were started by unless you did trickier things. So now let's do this again, but this time let's do it as my Father Linux user. Like you'll notice I'm not doing the sudo here. So let's do this. And then let's run the Docker one. And then again, let's do the grep-v. So you'll see here, there is something different. When you start it as Podman, it's pretty obvious that it started as the user Father Linux. But with Docker, it did start as root. Even though I ran the Docker command as Father Linux, it still went out, talked to the container engine, which is a daemon, and then basically fired off process from that daemon, which is running as root. Now, all the rest of the things are the same, though. You'll notice the SE Linux policies are all the same. In fact, that's because they share the same code between Podman and Docker. So you really can't tell. And then the only reason I created a special container image with the binary bash2 in it, just so that it would be easy to grep for, so we could do this real clearly. But there's nothing magical. That's just a symlink to bash, or I renamed it. I can't remember. All right, so let's go back. So this is a very simple demo to start off with. I jokingly say, raise your hand if you could tell the difference between Podman and Docker, which process was started by which. The tricky user will come back with the answer. Well, if you do a PS tree and you'll poke around, you can see, what the parent process is, and then you can tell who started it. That's correct. But you can't necessarily tell just from looking at the actual metadata associated with a process. All right, so let's go to 2. So this is where I'm actually gonna start a process from scratch. I'm going to start a container from scratch and build it up piece by piece. So Podman has some interesting sub commands that make it pretty granular the way you can start. And I'll run the rest of some of these demos with Podman here, just because of the way I can break up a container and start it by pieces. So in this first one, we're going to show you, like, we have, and this is true whether it's Docker or Podman or CRI-O or containerd, there's some kind of metadata storage, right? For Podman and CRI-O, that's varlib containers. For Docker, it's varlib Docker. It's basically a file system directory that has a bunch of stuff in it, whether it's config files or things that get created or files that get created when the containers get created. But if you think about it, it's two things. There's some container images cached out there, and then there's some metadata storage. And again, both of these things live in varlib containers for Podman world, and then they live in varlib Docker for Docker world. And this is with nothing running right now. So I'm kind of showing you what it would look like with nothing running. So now let's jump back to and show you. All right, so we're gonna do a create command. The create command basically just creates that metadata structure. It really doesn't do anything else, but you'll see it's pulling down the container image. It will actually cache that image locally. And then it will fill that it basically creates a directory. It caches that image globally. In this context, I'm running it as root, so it's actually cached in varlib containers. If I were to run it as myself, it would just be in Father Linux home directory in .local in containers. But you'll see here, after it gets done storing it, we'll take a look at like the metadata. I just wanted to show you that the create does pull the image. I actually, at the end of this demo, I delete everything to force this to happen at the beginning of this demo on purpose. So it'll take a second. Come on. There we go. Oops. So you'll see it actually gave me back a again, it gave me back a label for this. And then, that obviously created a directory in varlib containers. I think it actually matches this exactly. And then you'll see when we do a podman PS, which you can really think of like, if you want to think of like a PS as dumping the contents of the process table in a Linux kernel, you can think of podman PS or docker PS as dumping the contents of that metadata that's in varlib containers. And so you'll see here, it shows us we have one container created. It's in the created state. It's got some names, like we've assigned it things. We know which process we want to fire up. We know which container image we will use, but nothing's actually created. Like there's nothing actually running so far, right? There's no actual Linux process. So now let's talk about the next thing that happens. So again, we have this now. We have basically a copy on write layer created. Well, this is what we're going to end up with. We're going to end up with a persistent volume, a copy on write layer, and some metadata. So this is kind of what a container. This is kind of the next step in creating a container, right? So let's jump back. Podman has a cool. Oops, what did I just do here? I went to the wrong place here. There we go. I am in the wrong terminal. Sorry about that. Oops, I did it again. Apparently, if you hold that down too long, let's get out of here and go over it to manually. All right, so let's now look. So Podman has a pretty cool command called podman mount. And again, I give it that label, that metadata definition for that container that I've created, but it's not running yet. And then we're going to show that actually what it's going to do is go out and create this copy on write layer. So you can think of the copy on write layer is an extra layer that sits on top of the layers in the container image. The container image are essentially read-only layers. And then when you go to fire up a container, what happens is the container engine goes out and to the operating system and says, hey, give me another layer, to basically basically do read write data, to that. So if you look at what I'll do is I'll show you here because it's easier. If you look at this merged directory here, you'll see this merged directory. It looks just like a root file system now. And obviously I can go out and muck with this file system. So in here, I'm going to show you, I can go out and like actually go touch a file. There's no container running, but now if I look out here, you'll see that this file is actually out there. The test file's out there. And it's in you'll see it right here. The test file is actually out in that file system, but there's no container running again. So let's do a podman PS. You'll see it's still in the created state, which means, again, the metadata definition's there. We've now created a mount, a place basically to mount. You can, with Podman, you can do this mount, which basically exposes that mount that's in the namespace for the container and exposes it to basically the global, so that you can see it outside of the container. And that's basically what we're doing here with the podman mount command. And then we're mucking with it just to kind of do some hacky stuff to show you how it's going to work. Oops. So we'll go back and forth here because apparently I have too many tabs and things open. So here's where I asked a tricky question about performance, right? So like I have gotten all kinds of wacky questions about performance with containers before, and they ask me things like, well, how's the performance with containers? And I'm like, well, it's a copy on write file system. So if you're doing things like compiling a Linux distro inside of a container and you're doing that on a copy on write file system, you're going to have some weird scenarios there, right? Like if you're creating and setting permissions on thousands and thousands of files in a crazy complex hierarchy, just like a Linux distro does when it builds itself, you're going to have some weird performance issues. But if you do a -v bind mount, you're actually going to have like the exact same performance as Linux. So if you know how to use containers right, you should be able to basically get zero impact on performance. Like they should function at exactly the same performance as the operating system itself that you're using, the Linux distro that you're using. So it really shouldn't affect it, but it typically does because people don't do it right. That's actually usually the biggest problem is user error. All right, so let's go on to the configuration file that gets created. Again, I mentioned here, we've got some metadata storage. We've got our copy on write layer created. And now we're going to create a config file. So I say metadata plus the config. That's what the +C means. And then obviously I'd actually lie a little bit. I actually didn't create the persistent volume. I didn't do a -v bind mount, but if you had, that would exist now. Or it would exist once we basically start the container. And then I jokingly show this nasty drawing to like show what it really happens. So the first thing I did, the first question I got once I demoed this for somebody a long time ago, they went, well, what about the CNI blob? And I went, oh, what about the CNI blob? And if you think about it, basically, containers are interesting because really there's a person that goes and creates this container image, and then there's a person that runs this container image. And it's a collaboration. Like if you kind of work your way from upper left down to right, to get a running container is kind of a collaboration between these two people. The container image builder can put things in this container image like default config settings and things like that. And those get parsed and considered when you go to run the container image. Like you can literally set, people don't know this, but you can like set the IP address in a container if you want, in a container image. And the container engine will try to faithfully do that, or maybe it won't, depending on what the container engine wants to do. But if you think about it, it's really a collaboration between the person that's using it, the person that created it, and then the container engine itself. And so I show here image config, is kind of the first thing as the default. Then the user can override that. Then the container engine can add its own stuff. So like SE Linux policies, or so the SVert stuff in SE Linux automatically gets generated by the container engine. The user has no influence over that. The default seccomp file, for example, is controlled by the container engine. And the same is true on the networking side. So if you really think about it, it's actually the exact same thing happening to create this OCI compliant config file. And then the same thing is happening to create the CNI config blob. Now, this config file is compliant with container network interface, and this config file is compliant with OCI runtime. But then any binary that's CNI, basically a CNI compatible plugin will know how to consume that config file, and then the OCI runtime actually like runc or kata or whatever knows how to consume that config file. So it's actually not that complex, but it does twist your brain a little bit. And then on the file system side, I show you, all the image layers that come from the config, these are the read-only layers that come from the image. Then there's a graph driver. Then there's a root file system that gets created as like a copy on write layer. Unless you run the container as read-only, then this doesn't get created. But if you start to think about it this way, it really helps you like understand what's going on when you fire up a container, whether this is in Kubernetes or just plain Docker Podman. All right, so let's go back to over here and run this a little bit further. All right, so if you look again, we're going to look at this metadata. You'll see there's not much there. There's a SHM file and some artifacts. This is what's in that directory, varlib container storage overlay. This is our label for our container that got created. And then you'll say there's this user data directory. So this user data directory doesn't have much, but Podman again has an interesting, like the Podman mount command, actually has a command to just generate the config file. So now we can do this. We can give it that label, and it will actually go generate this config file. And you'll notice in this user data directory, we're gonna see that now once we've initted this container, initiated it, a lot of other things get created. Some log files, the config file. This is the interesting thing that we want to look at. And then let's take a quick look at that. So you'll see this config file is an OCI compliant, config file that basically will get handed off to runc or kata or any other runtime. And you'll see like all these seccomp file or all these capabilities and seccomp rules. These all get generated again by a collaboration between the container image builder, the image user, and the container engine. And essentially, there's all kinds of things in here. I won't go through them all, but if you ever want to dissect one of these, it's pretty easy to just grab it out of there once a container engine creates it, and then go look at it. And then you'll see still it's in the created state. We're still not running anything. We have a bunch of metadata created, a config file, a copy on write layer. We have all the pieces, parts in the OS kind of created to like basically start a container, but we don't quite have a container yet. So let's go back. So trick question. Do you think you could create these config files by hand? The short answer is kind of. I've actually hacked with this a lot to try to see. The thing is the container engine generates some dynamic labels and things in there, so it becomes kind of a pain. Like it will put C group identities in there and weird things. And so like if you try to run one of those with just runc by itself, typically the container engine will go and do other things like create directories. Like it creates that directory varlib containers storage overlay, like you got to, and then that big long label, it's got to go create that. So you'd have to go and hack and create that stuff because some of that stuff is coded in that config file. But yeah, you could kind of do this, although it's nasty and nobody really wants to create a JSON file that big. So generally it's probably best to just let the container engine do that. All right, so now let's talk about the runtime a little bit. So you'll see here, I lied a little bit in that there's actually a slightly more complex thing going on. Podman actually calls something called container manager, conmon, which then calls runc, which then talks to the kernel, which then creates a container. And you'll see below, I still show you, we have our persistent volume, hypothetically, a copy on write layer, our metadata plus the config file is all created. So now all that we really have to do is go fire off conmon. Conmon's going to call runc. Runc is going to call bash inside of our, inside of basically exec, or create a clone syscall and then basically make, the container fire up. But I want to talk about the double fork. The double fork is actually detached. This is something you can do in Linux. A lot of people don't quite understand. Like Podman actually calls conmon. Conmon forks itself and to like detach itself from Podman, because Podman goes away. It's not a daemon like Docker. So it does a double fork, and then conmon's parent becomes systemd, basically the init process. And then you'll see the init process direct child, because runc comes and goes. It actually just fires up and then disappears. And you'll notice that like in the end, you'll just have conmon and then the container running. So let's go to the demo and show you that. And this is where I think it gets kind of interesting. So this is when we do the start command. You'll see we pass that label again. We do start, and then we do a podman ps. And now you'll see we actually have it up for 1 second, like it's running. We fired up the process, and it's actually running. In this, though, here, let me do a little, I like to do this. So ps, let me get out of there and do a ps tree so you can see what this thing looks like. If you look, there's not a lot going on in this system. You'll see conmon, the parent of conmon, systemd, conmon's here, and then bash. So that's pretty cool. Like it's pretty simple. This bash process is basically just running with extra controls in place. And then conmon captures its console output. And then that's how you, when you fire up Podman again, it knows how to go talk to conmon to get data, basically to know what's going on in this container in a nutshell. Actually, technically it's in logs and varlib containers, but at least it knows how to do it. Like when you want to exec in, for example, you need to be able to go talk to conmon so you can actually get a shell in here. All right, so let's go back for a little bit more, because then we're going to start tearing this thing down. All right, so now you'll see we have systemd, we have conmon, we have container. I showed you that in there. And then raise your hand again if you think runc provides compatibility layer for running containers. So we've often confused portability, compatibility, and I also talk about something called supportability, which I won't bring here because that's more something that Linux distro vendors care about. But basically, in a nutshell, portability is what allows like the OCI image. Like I show a demo sometimes where I'll pull a Windows container down on Linux and cache it, and then you go to run it and it fails. The same is true if you like run an ARM. You can pull an ARM image on x86 and try to run it. It will fail. Sometimes even if you try to pull an image between Linux distros, they will fail depending on if there's like weird SE Linux rules, or when Fedora went from C groups v1 to v2, that will cause things to break. There's all kinds of weird scenarios where these things break, but compatibility is really something that's provided by the Linux kernel, and then portability is something that's provided by the OCI compliant, the OCI runtime and image format. All right, so let's clean things up. We want to kill. So this is what people don't understand a lot of time. If you run podman kill or docker kill, this is what you end up with. Like you'll end up with systemd running all that metadata there. The config file is still there. The copy on write still there. The persistent volumes are still there. But you can basically turn on and off these processes that are now missing from here, if you notice. And so killing a container is really not killing it. It's killing the running process, but you can fire it back up, right? So let's go back to there and show you what that looks like. So we issue the podman kill command. Boom. We do a ps-ef or -a. I'm sorry. I'm so used to Linux. You'll see it shows an exited state, right? But all the metadata is still there because it's showing up when we do the podman ps. You could think of the podman ps as, again, like I mentioned, dumping the contents of that metadata, right, in that directory, in this directory, basically in varlib containers. And so then let's look at the merged file system. Everything's still there, right? Like the file system's still there. If we were to look in Etsy, there'd still be that test file. We haven't deleted it. All that data is still there. If you had bind mounts, they'd still be there, et cetera, et cetera. And then let's do, I show you the config file still there, and a bunch of the, notice it doesn't go away. And this looks very similar to what we had when we first created the container, other than that config file doesn't get deleted. So let's go back. And then let's go to removing the container. All right, so now notice, look at the difference between these drawings. Notice I'm deleting the metadata, I'm deleting the config, and I'm deleting the copy on write layer. So if you go if you do a Podman RM or a Docker RM or a CRI-CTL RM or whatever, you will now realize this is what's happening, right? Like I'm actually just deleting that metadata, the config file, and then the copy on write layer. But the persistent volume will still stay there, right? Because it's typically bind mounted through to some other file system, be it local or somewhere else. So let's do a Podman RM, and then let's show you what this looks like. So now if we do a ps-a, there's nothing there. If we try to ls that directory, it's not there. If we do images, though, they're still there. So like the UBI or Red Hat Universal Base Image is still there in the cache. This is the read-only layers, like I mentioned, but they're still there because we haven't obviously deleted them. Now let's go on and go further. So like notice if we really want to start with like a really bare system and get it back to completely unpolluted, if you will, where there's no chance that anything could be messed up on the system, you now want to get back to where you just have an area that could store, you have a container engine, you have systemd and that persistent volume, right? So let's go back and jump to that. And obviously you do an RMI and delete these. And this should basically kind of blow your mind in that you're like, oh, actually, like RM should be called like kill, and like stop. Like you can think of these in very different ways, but the verbs that we have are the verbs that we have. And so it's kind of, it's more simple and less complex. I mean, it's more complex and less complex than you think in a lot of ways. But if you can think about it crystal clear, it's not that complicated. So with that, I wanted to like jump out real quick because I'll do like 1 minute here. I want to jump out. I do some commands to clean up the demo, but then I want to show you some other interesting, a couple little quick demos. I will sudo because I haven't tried these as a user, so I don't know if they work. But let's do like a Docker run. Let's see if we can start one. Actually, here, let's do a Docker run -it, and then we'll do UBI 8, and then we'll do bash. Actually, let's run this in the background. And then let's do a PS tree to kind of take a look at what's going on here. So yeah, something you don't notice here because it's basically impossible to tell because runc goes away. You'll see dockerd here fired off containerd, fires off containerd shim, which is basically like conmon, and then basically calls bash, right? And then if I were to exec into this thing, you'd be able to like look around, poke around in the file system, et cetera, et cetera. But what you didn't notice in the background here is that if you look at etc docker daemon, I actually have a couple different runtime set up. So I actually have crun set up. Crun is another OCI compliant runtime similar to runc. Runc is the reference implementation that basically everybody works on. It's actually the only piece of code that's part of the Open Containers Initiative. But you can write, any other OCI compliant runtime that you want, as long as it knows how to consume that config file that I showed you. This will work. So basically, I configured crun, and actually all these demos, it was pretty funny. Like I actually configured this and then made it the default for Docker because in Fedora 31, cgroups v2 became the default. So I basically wanted to use crun instead of runc because runc will fail out if it's running in cgroups v2 mode on a host. But I basically wanted to run it with crun. And so basically all the demos just worked once I basically configured crun to work. So that was pretty cool. And so basically you could use Docker and Podman side by side, and all of the things that you would expect from the architecture of having a separated container engine and runtime work. Another thing that you can do is quite interestingly, I got kata working with Podman, and then I basically just added this line here to Docker, and it worked with Docker too without doing anything because the kata runtime does all the work itself. And so I had to do a little hacking to get kata to work with the operating system. And to be honest with you, what happened is I'm doing nested vert here, and I had to hack around with that to get it to work. But once I got that working, it just worked. So for example, if we do a history grep Docker, you can see it's as simple as like this. Let's fire up like a process with Docker. And then I want to show you real quick what that looks like. So it takes a little while. This would actually happen pretty fast if it was bare metal, but I'm running in a Fedora VM on my laptop, so it takes a second to fire up a virtual machine. But if we do a ps-ef here, or ps tree, let's do a ps tree. You'll see similar to that, the dockerd is calling containerd shim. There's bash. There's my regular container, right? That's a process-based container. And if you look here, this is a VM-based container. So there's some more complexity going on. There's QEMU and kata shim and These things are all talking. VirtIO FSD is doing the pass through. So if I was doing the bind mount, that's how I would get data into the VM. So if I was like bind mounting, but it's all packaged up pretty nice and it's right here. And then the funny part is if I wanted to do this with let's exit out of this bad boy. And then if we want to do this with let's do a history and grab one for grab Podman. Um, you can do it just as easily as Podman. You don't have to configure anything to make Podman work. You can actually just pass it the binary with the dash dash runtime. So the interface is a little different than Docker, but same thing. It'll take a couple seconds to start the VM, and then once this guy's fired up, I'll show you. And then you'll do let's do a PS tree again, and then let's go look at Conmon. You'll see again, Conmon looks quite similar, right? Like all the same things firing up, right? Because once we call this kata shim, all these subprocesses and all these things get fired off the way kata wants it to. So you'll see these look pretty much identical. Well, it did look identical to what we fired up in Docker. The runtime does a lot of the heavy lifting, and you'll see the container engine just basically, like I said, creates a config file, and then the runtime goes and does a bunch of the heavy lifting. Another funny thing here we could do is let's get out of here. We can actually do like let's do runc. We could fire up one with runc too. Um, yep, we can't do it because we're in C groups v2. I forgot. Icat slash proc slash cmd line. We could put this Fedora box back in, but you'll see we have the system unified C group hierarchy. This is C groups v2. If we were to set this to 0, we could do this with Grubby because I've done it. Um, if we were to set it to 0 like that and then reboot, we'd actually be able to run containers with runc, crun, or kata, and it wouldn't matter. But I forgot that I put it back. I couldn't remember which way I had it, so I've been hacking around with it both ways. So yeah, that's kind of the end of my demo. And if you guys have any questions, I'm happy to answer them. Yeah, that's something I've been thinking about a lot lately for the same reason. Because like actually, when we build Podman, we have a ton of CI CD, and that's exactly right. Like the build speed with CI/CD matters a lot, and it gets annoying when it's slow. And so yeah, sometimes using a bind mount can speed things up like crazy because one, if there's something like, for example, I have one that a blog I wrote like 2 weeks ago about, of all things, I put a giant Perl app called Request Tracker because I'm old and I still use Request Tracker as my ticket system. And when I go to rebuild that thing, I do it with a bind mount. So Podman will let you pass a -v even if you're building from a Docker file. And so, for example, all the CPAN modules, Perl compiles a lot of stuff from scratch. So does PHP if you look at the pair stuff. And so having all that stuff pre-compiled in a bind mount is really, really nice because it speeds up CI/CD. It basically just checks all that stuff's already compiled and it reuses it for every container build. If like I don't need to rebuild that stuff, why rebuild it? So yeah, the short answer is I tell people to use bind mounts even for ephemeral stuff. The argument with a container, this was a person at a conference talked to me a couple years ago about Yocto Linux. That's when it clicked for me that people didn't understand the copy on write layer. They were compiling Yocto Linux inside of a Docker container on a copy on write layer, and they were like, "This is super slow." And I'm like, "Yeah, I would expect it to be super slow if you're like writing out tons of metadata, because copy on write is good if you write like one big piece of data, but if you're writing thousands of small pieces of data, that's when it gets like pretty clogged up." Yeah, so I'd recommended that they use a bind mount for that. Even if you don't care about the contents of the bind mount, still use a bind mount and maybe go and flush it every now and then if you really want to force a scratch build every now and then. I think that's you got to obviously do a little architecture there and figure out what you want to do for different types of software you're building. But yeah, basically. Yeah, so there's a couple different scenarios. So I use systemd a lot with Podman, and Podman actually has a generate command. It has a Podman generate kube and a Podman generate systemd, and it will generate a systemd unit file if you want it to like fire it up on boot. Like if that's the use case that you're looking for. Another is obviously handing it off to Kubernetes and just letting Kubernetes do that is another option. That's why we have the Podman generate kube. Another option, like if you're looking at like, but then there's other people that are actually looking to drive the engine as an API. For that, we're actually building an API right as we speak. The Podman team is working diligently on what we call API v2. API v2 will provide a REST endpoint that will be a socket-based activated service basically from systemd. Systemd will be the daemon, but you will be able to connect to it over TCP or over a Unix socket. And we will actually have two REST endpoints. One will be, I would call it 90% compatible with Docker because there are certain things they do that we can't do because we don't have a daemon. But it will be pretty darn close, and most things that you would talk to a Docker daemon will probably work. And then we will have a Podman specific one that has all the Podman API endpoints, like because there are certain things that Podman can do that Docker doesn't do. We do have, if you look at the syntax between them, the subcommands are not exactly the same. They're probably 90% the same, but they both have a little bit of differences here and there. So like the Podman API endpoint, it will be REST based. It will look a lot like Docker, but it will be its own specific thing for Podman. So if you're trying to drive an engine to do like scripting, like say you scripted things, that's probably an option.
Okay. How about you demoed CRI-O? How is it stable enough to be used in production already, or?
I wouldn't recommend production, but it is really cool. It's tiny and it's written in C and it's super fast. So I'll say from Red Hat's perspective, we're looking at it pretty seriously. We want to build more of a community around it and see that it can stand on its own and have community support. It's written by this genius guy Giuseppe at Red Hat, Scrivano. He's awesome, but we want to see like a few more contributors from outside of Red Hat. Like Red Hat really does try to do community-based open source. We don't like to just lead customers down a path where it's like a single project that only we're contributing to. So we're looking at it. We may include it in like Red Hat Enterprise Linux as an option. It's already an option in Fedora. But being very transparent, I wouldn't recommend it for production yet. But I would say play with it. See, I mean, to be fair, there's not that much that can fail with a container runtime. I mean, as long as it will talk to the kernel and fire up the process, like say you're firing up a process once a day, then it's fine. But if you're running Kubernetes, I wouldn't recommend it for that because Kubernetes restarts containers all the time. And that's where I might get a little bit hairy about whether it runs, crun is production ready or not. Do you have millions of containers firing up with it? And that's when it would fail, right? Like is during the startup if it were to fail.
So which one do you recommend to use with OpenShift, for example?
Oh, we use runc because everybody else on the planet uses runc.
Okay.
We're looking at down the road. We're trying to actually add cgroup v2 support to runc, and it looks like that's going to happen. And so, I mean, that'll make runc be able to do everything. But we are looking at use cases where like we might integrate crun in Conmon, have a single process that doesn't have to exec, and our startup times might be able to be super fast. So we're looking at use cases where performance might matter, where you might be able to use crun as like a super fast way of starting up a container. But for now and for the foreseeable future, OpenShift will use runc.
And do you still use Docker inside OpenShift?
Not in OpenShift 4. OpenShift 4 uses CRI-O and it uses runc. In OpenShift 3.11, which will still be supported for a long time, it's using Docker on RHEL 7, but it's an old version of Docker 1.13.
Okay, well, it doesn't make a big difference, I guess. As long as you use Kubernetes, the user doesn't have to worry about whatever is taking care of containers. Right.
Yeah, and that's kind of why I showed this demo of like how the container engine works, because I think people were scared. It was always a black box to almost all of us, including myself. And it's genius the way it's all architected, but it's cool that you can tear out pieces and like optimize them for what you want. If you want a VM here, you can fire up kata. If you want regular containers here, you can use runc. If you want super fast starting containers, you can use crun. You can use gvisor. You can use all these other things too.
Nice. Let me see if we have a question from the audience. Yeah, so someone is asking, concerning container security, is it better to run them using Podman rather than Docker?
That's a tough question to answer. I mean, we think obviously there's security advantages depending on how you run it, right? Like if you run it rootless, if you Google my name and root in a container, there's a lot of different ways. You can lock down Docker containers pretty well if you're careful. What happens is most people aren't careful. And so they run them as root. They pull down container images that need root in the container. And this is just like become a standard practice. It's definitely not a best practice, but it's a standard practice. And so when you do that, I would say then Docker's not as secure as Podman. But if you were to like force those containers to run as like an Apache user or a non-root user, you can basically control, pretty well. The question is it's like it's defense in depth, right? Like I want non-root outside the container. I don't even want to have to fire it up as root. Then I want non-root in the container. And if I have non-root in both places, I'm actually in the best. That's the most secure. But if I'm going to have root outside the container and then non-root in the container, that's pretty good still. Docker can do that. But if you want non-root outside the container and non-root inside the container, Podman is the only one that can do that right now. Even CRI-O runs as root, and so does containerd, and then they can fire up non-root containers inside, that run as a non-root user. But in a perfect world, you want non-root everywhere. You want it inside and outside. The worst case scenario is you run root outside and root inside, which is a super privileged container. You're basically, if you run -- privilege, you basically have root in and out, and then that's the worst because then the human being can completely hack your system. If you turn on -- privilege, that's obviously bad. I mean, that's not a container anymore. That's just a regular process that you fired up from a container image. So that's bad. But yeah, I have an article here. Actually, maybe I'll bring it up real quick. Root inside and outside of the container. Let's do this here. I'll share my screen real quick if you want.
Okay.
Here's an article I wrote on that probably would answer. You would kind of understand like whether it makes sense or not. But this is kind of how I break it down as a table. I show it with Podman. You do who am I outside, do who am I inside. This is the least secure. This is really bad. This is running, privilege basically. And then if you run it, if you run root here, outside or not user root inside, and
I cannot see your screen right now.
Oh, you can't? Oh no. Let me unshare and try to share again. Entire screen. Let's try this again. It showed it sharing.
Yep.
Now it's showing?
Yeah.
Okay.
Oh.
So this is the drawing that I came up with, or table that I came up with for this blog entry. But if you look, this is the least secure in the top left. This is the most secure in the bottom right.
Still can't see it. Sorry.
Oh no. Darn it. Here, I'll send you the link.
Okay.
I don't know why my screen got messed up.
Got it. I'll just show it to people.
Yeah. And then if you show them, you'll see there's a table, like just a little bit down if you scroll.
Okay, I can see it.
Yeah, and then the top left is like the most secure, or the least secure, I'm sorry. Then the bottom right is the most secure. So if you can run it as Father Linux outside the container engine and then run the process as a user, like sync, that's the best, because now the hacker would have to break through that sync user, get outside the container, and then break out of your user account and then break into root on the host, right? Like this would protect the host the most from any kind of hostile workload. And then obviously if you want more than that, you can do kata containers. But I would argue if you can run things in this bottom right way, that's pretty darn secure. Now, again, only Podman can do that today. All the other ones run as basically the closest you're going to get is this left box. Inside user is a user, but user inside, but it's a root outside. That's pretty much what you get with Docker. And the other problem is like in Docker, it has all of the permissions that you need to build a container image, whereas with CRI-O, it only has certain capabilities. I think it's got maybe like 7 capabilities enabled. And I want to say Docker has like 13 or 14 enabled. So like you can still limit it even if you run it as root. And then that again helps break out. So a lot of this gets into nuance, but it's like, it's risk tolerance, right? Like, and how risky do you want to get? But for example, if you're running Docker with kata containers and Podman with kata containers, you basically end up with a wash. Like kata is what's doing the locking down. So you're going to have QEMU level isolation. So that's good enough for almost anybody. So I think it just kind of depends on what you're trying to do.
Okay. I cannot see our face anymore.
Nope. Let me. Oh, really? Oh, must have. I could refresh my Hangouts if you want.
Okay.
How about now?
No.
Nope.
What do you use for video conference usually? Zoom?
Who, me? We use Google Hangouts a lot, and then we also use or Meet, and then we also use Blue Jeans a lot.
Okay. Did you ban Zoom?
No, we still use Zoom a little bit. I mean, the problem is so many people are using Zoom that sometimes you have to join them for other people. But I think, my understanding, I'm not a massive Zoom user, but everybody's now doing this thing where they have like a waiting room, and then you only let people in from the waiting room. And I've heard that's decent security, but.
Yeah.
Can you see me or no? Can't see me still?
No, still not.
Yeah. Well, I don't know if we have any other questions anyway. Maybe if we don't have any questions, maybe we could end anyway.
Yeah, we have one question that I think you kind of answered it. I'll say it anyway. Why is there runtime Podman and CRI-O, and what are their differences?
Yeah, so CRI-O is specifically a daemon. It is a daemon. It's a very small daemon that has limited capabilities, and it's made specifically for the kubelet. So I mentioned there are container engines that are kind of optimized for humans to talk to, to run commands, and then there are container engines that are optimized for robots to basically go talk to, their APIs basically. Container D and CRI-O are basically specifically more for robots. So Container D is sort of a general purpose one for robots, and then CRI-O is a specific one only for the kubelet. Like CRI-O is not meant to be used with anything other than the kubelet, and so it tracks the kubelet exactly. So like CRI-O 1.13 is supposed to be used with Kubernetes 1.13. When Kubernetes 1.20 comes out, CRI-O 1.20 will come out, and so the versions of CRI-O map to the kubelet and the kubemaster, as it goes, it always versions with it. So it's basically a container engine dedicated specifically to Kubernetes.
All right.
With no other users.
Okay.
And then Podman's a general purpose one for people to use, and anybody that wants to do anything. And then once we add the API in V2, it'll even have its own little API, its own API, but that'll be optional. You don't have to turn it on. It's socket activated by systemd, or it will be socket activated.
Okay, makes sense. All right, so it looks like we don't have any more questions. Is there anything you would like to ask on before we start the stream?
No, I think I'm good. I had fun. I love going through this stuff, so I'm a nerd.
Okay. Well, thanks everyone for watching, and don't forget to subscribe to the channel, and see you next time then. Cheers, bye-bye.